Sorry. So hello everyone. With the continuation with the previous lecture, now we'll be discussing the actual scenario of uh, transmission line. Okay. So before going to discuss this equation we got, you remember this potential is V rho L 2 pi epsilon naught ln R1 by R2 and rho L 2 pi epsilon naught ln modulus of K. Okay. So these things we got. Okay. So C equal to rho L by L. L may be considerable as the line length of transmission line. Okay. And this is the V. Okay. So now just simply I am presenting suppose a transmission line, and this is the actual case. Okay. So this is you can consider as origin, and suppose this is the x-axis, y-axis, this is the z-axis. Okay, and here with some radius, this R, the radius of this conductor and this conductor. So firstly, maybe one question will be there. So in previous lecture we have discussed about the line charge distribution, but here the line charge distribution may not be for conductor. Okay. There are many charges, there are surface charge density, line charge density. Okay. What will be considered? Volume charge density. What will be considered for this case? Okay. So let a fixed potential V be applied between two conductors. So we are considering this conductor and this conductor, and their potential between this and this is V. Okay. So that the charge per unit length of the conductor is rho L coulomb per meter. The length of the line is very large as compared with the distance separation. Length of the conductor, suppose length of L, and this is very large with this, and also age is large about the radius of the conductor. Okay. Length is very greater than whatever the separation between them. Separation between them is what? G. What? This separation was how much? S. This separation was how much? S. So S is nothing but what? G. From the equation what we got? G is what? K square plus 1, K square minus 1 into S, these things. Okay. Where? And what was the R? R was 2Ks and K square minus 1. 2Ks, K square minus 1. These two things you should remember also. So this R and this R is okay from this origin. Okay. So now take any point we have taken, the P point. At that point आपका location देखना है, ठीक है. So now if we see the ratio between this G and R, what we'll be getting? We'll be getting k square plus 1 by 2k. Okay, just we simply divide this g and r. So this k square is so SS will be cancel out k square minus 1 k square minus 1 will cancel out. This will be cancel out. So there will be g by r k square minus 1 divided by 2k. So from there we will able to calculate k as 2hr. Okay, plus minus 4a square r square minus 4 divided by 2 into 1. Okay, so now simply you can see that k will be the h by r plus minus a square r square minus 1. If we consider that h by r is greater than 1, much greater than 1, then what? The k equal to h by r plus h by r. That means 2h by r. Clear? Now we can consider that this k is the value of k not equal to 0 and positive for the positive value. What? The capacitance is what? Rho L into L by V. Okay. Now this rho L into L, and here the V is what? What was the V? V is nothing but that rho L 2 pi epsilon naught ln k. Now this capacitance we can consider that this length is considerable. We can consider it the per unit length capacitance. Per unit length capacitance. Okay. Per unit length capacitance. Okay. So the farad per meter. So C is nothing but 2 pi epsilon naught h by r plus a square r square minus 1. So this equation is what? This equation is actual equation. Okay, but approximately C is 2 pi epsilon naught by 2h by r. So this cancel. So pi epsilon naught r by h pi epsilon naught by r by h is equation. Will be getting. Okay. no, no, sorry, this one more thing is included, this A, ln K, okay, ln K, so see L, right, rho L, L, first we consider the per unit length of capacitance, L will not be there now, rho L cancel out, 2 pi epsilon naught, capacitance per unit is 2 pi epsilon naught, what, the ln K, K means HR plus under root A square R square minus 1. Okay, so these things will be getting, okay, clear. If H much greater than R, 1, 2 pi epsilon naught ln 2H by R. Okay, ln. So this expression is for 2 pi epsilon naught ln 2H by R. This is for actual one. Okay, actual calculation for the capacitance calculation, capacitance per unit volume. Okay, now we will be discussing about some points on this, why we will be considering as this rho L distribution along this transmission line. Okay, so rho L coulomb per meter distributed on the surface of the conductor, which may be considering as which is non uniformly distributed over the surface. Okay, non uniformly distributed over the surface, non uniformly distributed over the surface. Okay, over the surface, such that it has the higher density on adjacent side of the conductor. Suppose this is the conductor. Okay, suppose cylindrical type conductor. Suppose cylindrical type conductor. Okay, so it has the higher density on the adjacent side of the conductor. The adjacent side, this suppose surface, this suppose surface. So this charge distribution can be considered as the line charge. Okay, so this will be considered as a line charge. Okay, okay. The surface of the conductor represents surface of the conductor. This surface or conductor, this type of conductor is represent the equipotential surface. As we previously saw, the equipotential lines. Okay, so equipotential lines as we seen in previous lecture. Okay, so so the objective for this lecture is that will to be find out the equivalent line distribution for the system of two conductor with the operating voltage P. Distance of separation was H. So what was given in there? So this was the conductor we consider this was this conductor. So this was the radius, this was the radius. So somewhere the center to center conductor distance was G. Okay. So anywhere along this line, anywhere P, if we consider, so from this point to this point, if distance of this, y you can consider, and from this to this, and the distance is G minus y. Okay, G minus y. So as we calculated this expression 2 pi epsilon naught ln 2 pi hr, this is for the non uniformly distributed case. Okay, this case is discussed for the non-uniformly distributed case. Okay, but now we will be taking consideration with that uniformly distribution of charge, uniformly distribution of charge. What will be the concept? We can simply calculate the E positive due to this E positive rho L 2 pi epsilon naught, how much? G minus x, and for negative charge it is about minus rho L 2 pi epsilon naught y, in the direction of what? Y direction, and here also this direction of y direction. So this plus rho L and minus rho L, these are in by opposite in nature. So what will be the resultant? Resultant will be the attraction force, like attraction force. So this is the resultant, E plus and E minus will be the attraction force. Okay. So total attraction force will be this direction will be minus rho L, this direction, this way. If that is in y direction, this will be minus z direction. So what will be the resultant? Resultant is rho L 2 pi epsilon 1 by y plus 1 by G minus y. Clear? So now the potential difference, and is also the potential difference. Potential difference will be G minus y equal to G minus y to R. Okay, G minus y to R. Okay, E into dy. Okay, along y. So finally you will be getting rho L by epsilon naught ln G minus R divided by R. Okay, if G much more greater than R, so G minus R is equal to almost equal to G. So the actual potential will be rho L epsilon naught ln G by R. Okay, so this equation we can calculate. Okay, and equivalently C will be the rho L by D is by epsilon naught ln G by R. Okay, that is farad per meter. Clear? So the equation this show corresponding to the expression for the capacitance of single phase transmission line. So this equation shows the mathematical presentation of single phase transmission line. Okay, so as this concept also we can present, sometimes it is required to know the capacitance between one conductor and a neutral point between them, so which will be the defined as a charge on one of conductor per unit of voltage difference between the neutral of the conductor. This means the capacitance of one conductor with respect to the neutral plane is 2 times the capacitance of single phase line. Okay, again I am telling, sometimes it is required to know the capacitance between one conductor and neutral point. What we have discussed this, if it is rho L, if this is plus rho L. Okay, so between this and this, what is that? And somewhere suppose this is the origin. Okay, so this plane obviously will be the zero potential point. So this point is nothing but what we can consider as a neutral point. Somewhere here we can consider the neutral. Okay, so here simply we can represent a neutral. Okay, so between them which will be the defined as the charge on one conductor per unit of voltage difference. Suppose here voltage and for this voltage. Okay, this voltage difference between this point to this and voltage difference between this point to this. Okay, this point to this. Okay, so this is the negative potential, this is the positive potential. Clear? And this is the neutral line. Okay, so this means the capacitance, this means the capacitance of one conductor with respect to the neutral plane. So this is the conducting plane is considered as a neutral plane. Okay, is 2 times the capacitance of single phase line. That means simply it's presenting what? Simply it is presenting the series combination. The series combination of this is line. Okay, suppose one conductor, E conductor, this is the neutral. Okay, So CN and CBN. So CN, CBN, so resultant capacitance is CN into CBN divided by CN plus CBN. So these are the almost equal. Okay, C by 2. Suppose C dash by 2. So C dash is 2 times of C into CAB. Okay, CAB into CNAB. So 2 times of this equal to capacitance. Means only 2 times of this. So do this CAB. So for this CAN, what will be the pi epsilon naught 2 ln h by r farad per meter and also CPA is capacity. Okay. So just we want to see the view for this lecture. What we discussed. We have discussed the two-phase transmission line. Okay, two-phase transmission. That means that presents the single-phase line presentation. Okay, single-phase line presentation. Clear? So with positive charge, two bipolar line charge distribution is presenting as a line conductor. Okay, as a line conductor. So there would be the distribution of charge on the surface of the conductor, which is non-uniformly distributed over the surface. Okay, such that it has the higher density on the adjacent sides of the conductor. Okay, and we have seen in the previous lecture what we have seen. We have seen the radius equipotential lines. Okay, and here we have discussed the for in case of non-uniform case and in case of uniformly distributed case also we have seen. Okay, so this is about the line capacitance for the single phase line. Okay, so this lecture you should remember. Okay, it will be useful for your higher course of power system. Okay, so you have to remember these things. Okay, there is a concept of line charge, there is image charge. Here what we have discussed. Firstly, we discussed the electric field intensity. Then what we discussed, the potential. If any 2 points between electric field intensity due to the due to line charge distribution, then okay, they are symmetrically represent with symmetrically located at with respect to origin. Okay, then what is the potential, total potential? We have used the method of images, and we calculated the equipotential lines. Okay, equipotential lines with there is a consider the ratio is R1 R2, and we have considered one ratio, means one radius of equipotential lines. Okay, so that is small r is represents by equal to 2 ks by k square minus 1, and also and the center at we consider the y equal to 0, x equal to 0, means g equal to 0 and g equal to k square plus 1 k square minus 1 into s. Okay, that thing we discussed. From that concept of bipolar line charge, we imposed into a single phase transmission line. So there single phase transmission line also, what they are spacing distance between them is g. Anywhere any point is there, so that point is from one point to conductor to that point and another point. Okay, so here this conductor, so this conductor we have calculated, this conductor we have considered. So from radius of this conductor is r, radius of this conductor is r. So spacing between this conductor we have considered g. So any point we have considered that this point p. So from this point to this point distance is what? We consider that this point is y, and for this point to this point is g minus y. Okay, from there we consider the uniformly distributed charge if there. If the line charges are distributed uniformly, so what we do? So in practical case, it is basically the distributed line charge only. Okay, for long transmission line, suppose long transmission line, short transmission line, medium. This is not just 1 and 2 meter per meter. Okay, this is 100 kilometer, 200 kilometer, 300 kilometer matter. So it will be considered as a uniformly distributed matter. Okay, so from there we calculated the C also. Okay, and from there we have calculated the with respect to the neutral plane, with respect to the neutral plane to share from the image of method of image. We know this, if this is positive, this is negative, and they are symmetrically spaced. For this effect there will be a zero potential line, so that is the neutral lines will be same. Okay, so this is the concept about the single phase capacitance. Okay, one more thing, the capacitance is a shunt element of transmission line. Okay, so this element capacitance, inductance, resistance, these are the practical parameters to study the performance of lines. Okay, transmission line. So I think I have given all the information about the capacitance calculation. Hope you understood. Thank you. We'll meet again.